So we are starting the fourth lecture by Sylvie Méléard.
So remember yesterday, so we I think that is the sound good, no? Because it's there is some resonance. Okay, thank you. So yesterday I showed you the first choice of scales between mutation scales and time scales, allowing to obtain some mathematical candidate to which can model the evolution in a certain sense. And we have seen that from this point of view, if the mutations are very rare, then the process at this time, the mutation time scale will converge to a jump process going from one equilibrium to another one. So it's really a sort of multi-scale problem. You have different time scales, and at the end you find such sort of process, which was called by Hans Metz the trait substitution sequence, since at any step should substitute the old resident trait by the new one. And at this velocity, and we have seen that this fitness S of Yx plays a main role. So I would like to show you how does it work through an example. We take a very simple example, but that we will follow during the two lecture, which is to take the trait x in a finite set. Here it's 0, 4. B of x is 4 minus x. So take x can be some size trait, for example. So yeah, and we have seen that if it is related to the quantity of plasmids, then it's costly, and then the growth rate will decrease when x is increasing. And so you have a fixed death rate d1 and a competition pressure, which is a constant. And so remember that S of y x is equal to Ry minus C of xy times the equilibrium n bar x, and n bar x is equal to R of x over C of xx. We have seen that yesterday. And then if C is constant, so you have only R of y, so of course plus, sorry, the transfer flux. So we have R of y minus R of x, which is usual invasion fitness, plus the transfer flux alpha of yx. So for the moment, we assume that alpha is equal to 0. Either tau is symmetric or tau is equal to 0. And in the case of invasion fitness is given by this expression, and I remember that I explained that this fitness will govern the outcomes of the dynamical system. And so we have seen that Y will be able to invade the population if and only if f of yx is positive. And that means f of yx here is x minus 1. And then Y will invade the population if Y is less than x. And so we can imagine that, so you see that the evolution will lead to the optimal trait, which is 0, the trait which increases the growth rate, which is maximum, okay? So we made simulation with some value which are here. So the variance of the mutation is so the mutation is a Gaussian with a variance sigma square, and we have initial individuals with trait 1. So at the beginning, x is equal to 1. So the population size is k times n bar 1. That is 1,000 times r of 1. So r of x is equal to 3 minus x. So times 2 over 0.5. The constant, that means 4,000. Okay. And so if we go to the optimal trait, so what would be the population size for the optimal trait? It will be k times n bar 0, which will be 1,000, 3 over 0.5, so it's trivial, so it's 6,000. So it's to explain the simulation. So now I show you in this case the simulation. And so all individuals at the beginning have the trait 1, and you have in the color, you have a right, all the individuals, as you see, it's right at time 1. So we have 1,000 individuals at time 1, and we have mutation. And following the mutation, so you see that as you assume, you see the evolution of the trait of the population going to the optimal trait 0. And so that's the curve for the mean trait. So time is on the horizontal axis, and the trait value is here. And here you have the evolution of the population size. So you see that very fast you go to n bar 1. You are at the equilibrium 4,000, which is the equilibrium for the trait 1, 4,000 individuals. And then after, when the trait arrives close to 0, your population size will fluctuate around 6,000. Okay, and so that's the histogram of the trait values at this point. So we are not exactly, so you see that there is a big peak around 0. Okay, so now we are transfer, and so we will take a unilateral transfer. That means that we will transfer from y to x if x is larger than y. So that means that there is a real trade-off between the growth rate, which will advantage small traits, and the transfer, which will advantage the large traits. Okay. And so the fitness now is as this expression, so x minus y plus the tau. So we will play with this parameter tau times the sign of y minus x. Okay. And we can see that the fitness which governs the outcomes of the dynamical system in this case, the fitness is positive. So if and only if you have two cases, either x greater than y and x minus y greater than tau, or y greater than x and tau greater than y minus x. So if tau is small, this situation is possible. But remember, x minus y is the order of sigma. That's the mutation step. Okay. See, if tau is really larger than this mutation step, you will not have this situation. You will have this situation, which means that the evolution will drive the trait to larger and larger trait. But of course, if the trait increases, the growth rate will decrease. And so, in particular, the reproduction rate will decrease. And so, with large traits, you can imagine so that first evolution will lead the population to larger and larger trait, but it can go until what is called in evolutionary suicide. That is that the population will go to extinction with the size. So we have simulation. So here, tau is almost of the order of the mutation step. And what we see is that what we were waiting for, that is, we have essentially the same picture as without transfer. That means that the population will go with slower time to the optimal trait 0. So you see that on the same time interval that takes a longer time, but essentially you have the same picture, and you go from 4,000 to 6,000 with okay. So now we consider a large transfer rate, which is 1. So 1 is 10 times the mutation, the order of the mutation step. So we are not. And here what you see is really this evolutionary suicide. I mean that because the transfer is stronger than the demography in this case, and so you will by transfer you will. And of course, the play between mutation and transfer, you will select individuals which are with a larger and larger trait. And you see that the growth rate is 3 minus x. So when s becomes around 3 or even larger than 3, you will go to extinction because your growth rate will be negative. It will be subcritical. And that's exactly what we see. Here you have the increasing of the mean trait, and here you have the population size, which go to a certain value and then go down until extinction. Okay. So what happens between both? And so we made simulation with this rate, 0.6, and we obtained this picture, which was really amazing. And I think that I will take the end of my professional life to understand what happens mathematically, I say. And so you see that you have the transfer is winning. First, that means that it pushes the individuals pushes the evolution to select individuals with larger and larger traits. But so you have the mean trait, but in the same time, so here you have this 4,000 people, and then of course, since the traits are increasing, the population size is decreasing. Okay, and it's decreasing until this, but you see that until you arrive here, when the trait is large, since the growth rate, especially the birth rate, is very small, you don't produce a lot of individuals. Okay, and then if you keep, and if in your setting you keep individuals with optimal traits, a very few number of individuals with optimal traits, which have not been transferred. Okay, they were not in contact with the individual alive here, and they are here. I don't know if you see them, but I see they are here. And when the population here is small, it does not push enough, and so these individuals can survive, and then they will develop their own strain, their own subpopulation. Okay. And so you have this sort of here. I think it will be cyclic after a certain amount of time. We will see the next simulation, because here you see that you have strains, and you select finally the initial individuals of these new strains have more and more adapted traits. Here we have a 0, and okay. So. So our aim is we really would to understand this brutal appearance of new traits, and of course this cannot. You have remember the mutation step is 0.1. Here we have more than one jumps that cannot be explained by mutation. Okay, and so I show you. So we have this situation. What happens when we increase this transfer rate? And so here we have this tau, which is 0.7. We have exactly the same. I mean, there are 4 simulations of the same problem. I mean, and you see that you can have either this cyclic phenomenon or the evolutionary side. So that means that that's very delicate, because really the fact that you obtain such sort of picture is related to the fact that you keep individuals alive, keep individuals with smaller traits alive in your population. Another way to see that, so this simulation were done by some master students, and so with a group of PhD students, and with Vincent, we tried to make some numerical research on this, on all these cases, as CPD explained yesterday, on Monday. And in particular, if you look, so here you can see it's more or less visible, but you have these strains which appear here. And if you look for the lineages of the individual alive at a certain time, you see that almost immediately it is explained by the individual with the smaller traits. Okay. So the question we have now in mind, which is fascinating from the probabilistic point of view, is how to keep track of a very few number of individuals in a large population approximation. So because okay. So we so what can we see here is that in the simulation we took a mutation probability 0.03, so it's small, but kpk here is not small. Okay, so and also yes, the time before emergency seems short. So we are not in the previous assumption. That means the time scale has to be shorter and the mutation probability is large. Okay. So we will first. So we first try to develop some model based on probability, stochastic, and you will see that it's not so easy. And our aim here was to understand the first re-emergence of the optimal trait. Okay, so the idea is to be in a sort of scenario where we are only on this situation. So we have an optimal trait as 0, that will be the initial condition, and we try to understand how this second strain appears. Okay, and so we took a very simplified model, and so that's work with Champagne and Tran, and so first we are unable to keep information on a finite number of individuals, but we thought that it could be possible to find subpopulation of size k to the beta less than 1. Okay, remember that k is the order of the dominant population size. But we would like to keep track of small population of such size. Okay, and to do that, we were obliged. So for the moment, we have discretized the space. So with discretization save delta, which will be fixed here. And so we consider this model. So we develop this, and we observe that there is this choice of scale has already been done in a paper by Dorret and Maybury in 2011, and also we work essentially during the same time without discussing together. But there is a paper by Bovier, Coquille, and Smady which considers such sort of case for a problem of fitness valley. And now there are also a paper by Rohrenblatt and co-author concerning seed bank models using such scales. Okay. So the idea is here, and to know exactly to describe the subpopulation, we discretize the space. So we take a simple model where we have this finite number of traits, and we consider a mutation probability k2 minus alpha, with alpha strictly between 0 and 1. Okay, so now k to the 1 minus alpha, which is the population mutation rate, tends to infinity. So that's exactly the situation of the simulation. Okay, so we take exactly as in the simulation. So we have a constant competition pressure and a unilateral frequency dependence transfer rate. And then, as we said here, the fitness is, so we will keep this expression of the fitness. That is x minus y plus the tau, the sine of y minus x. Okay. And we consider, as I said, we are in the situation where we consider, so 0 is the optimal trait, and at the initial condition we have individual at 0. So at and there are at equilibrium. So we have 3k over c, that is the value for 0 at the equilibrium of the population size. Okay, but since we have remember the mutants arrive very fast because k to the 1 minus alpha tends to infinity. We can assume that almost immediately you will have, if we have trait 0 with a population size of order k, you will have almost immediately k to 1 minus alpha individuals for the next trait. I forgot to say that here we impose for the mutation, it's directed. So we go from x to x plus delta, okay? Because you only want to understand this reemergence, okay? And so immediately you will have course, the initial condition K1 minus alpha, K1 minus alpha, that means, and etc. And you can go until this exponent becomes negative, and then it is 0. So we have this initial condition. We want to understand the behavior of this small population of size k to the beta, and we observe that if the population size for a trait I delta is k to beta ik, so of course beta ik has this form. So since n we can go to extinction, we are the one to prevent extinction here, and so we consider this exponent, okay? And we would like to know what is the the asymptotic behavior of this process when k tends to infinity on finite time interval, okay? But here we have changed the time scale of the population size, and we will see why in a minute. It's related to the population. We know that the population size will be in exponential of the growth rate for times the time. Okay. So we will look, as I said, this process, the process of the exponent on the time scale logarithm of k. So now the individual mutation rate is k minus alpha, and the time scale is logarithm of order logarithm of k. So the first, unfortunately, I will not have time to give the proof, but they can be helpful in other situations. So first, you consider a small population with trait y in a resident population with trait x larger than y. So in this case, from the point of view of y, its subpopulation will be a branching process with birth and death rate. So 4 minus y, which will be the birth rate for the trait y, and the death rate, so it's 1 plus the competition term plus 2, because you only transfer unilaterally, and x is larger than y. So y can be an individual with trait y can be changed in an individual with trait x, but it's not, the contrary is not possible. Okay. So the question here is, you have a linear birth and death process, so a branching process with rates b and d starting from the initial condition k to the beta, or k to the beta minus 1 if you want that k0 is describes the extinction, nevertheless. So this process converges uniformly on time and in probability to beta plus s b minus d sup 0. So that's not surprising, of course, since you know that if you consider the expectation, if the initial condition is beta of this process, this birth and death process at time t, it's k to the beta exponential to b minus d t. The expectation. Of course, here I speak about the trajectories, but and if you take it in logarithm of k, that will give you k to b minus t. Sorry. So the exponent here is not surprising, but in fact, the proof to obtain this convergence in probability uniformly in time is not so easy, and especially you have to control the possible extinction events. And since here we did not make any assumption on b and d, so b minus d can be negative. Okay. That's why we have this supremum with 0. Okay. So that's the first lemma we will need, and there is another one when you take y greater than x, and you assume that now the mutant, if x is the resident population, and you have a mutant, and the mutant is x plus y, plus delta, sorry. So it will be greater than x, and you will have possible transfer from x to y, okay? But not in the other sense. And so now, for the point of view of y, the birth rate will be 4 minus y plus 2, and the death rate will be the standard death, okay? But that's the main point. But as we have did, in fact, to compute the initial condition, you have the transfer, but you will also obtain a contribution by mutation. So it's an immigration from the population from the resident population with trait X. Okay, so this population, so that will be at time t. You have the population size of individual with trait X, which is nkxt times the mutation individual rate, which is scaled to minus alpha. Okay, and so this quantity in the scale logarithm of k that behaves as k to c plus some constant c plus some constant a times s. Okay, so we have to add in the previous lemma some immigration, and so the second lemma is that with the previous assumption and adding an immigration at rate k c exponential at, and so we can see that if you consider this process, and so if you assume that either c is less than beta, so that there are situations that we will have in our population process, so you converge exactly in the same sense, uniformly on time in probability to so that's the exponent we were waiting for without migration, supremum with the term given by the immigration, or supremum 0. And so essentially you can have different situations. So here you see that first all is negative, so 0, so you have the exponent at 0, and then you have the first, here you have the assumption is that beta is greater than c, strictly greater than c, and small a is less than r. So this part is winning, you can say, and we follow the first line, and the other line is on. Okay, but when you attain 1, you have the dominant. You are at the dominant population level, and you are that 1 means that the population is of order k. Okay, and so that's the second situation where c is always less than beta, but r is less than small a. So r is b minus d. That's the growth rate. And so this slope is less than this one. And so at the beginning, you follow this quantity since beta is greater than c. But at some point, you are driven by the immigration process. Okay, and then you attain 0. And in this one, so you see that you have this decreasing fitness, since R here, the growth rate is negative. And but you could think that you will go to extinction, but due to the immigration, you can have a sort of re-emergence, and then the exponent will be driven by the immigration quantity. Okay, so yeah, you see that playing with these different parameters give different behaviors. So that's the two first lemma, but that took a certain number of pages to prove them, and but there are essential bricks, essential steps in our. So it's very hard to give you a complete proof, but I would like to show you how we can use such sort of dynamics only with a case of a very simple, it seems simple case of 3 traits. So 0, delta, 2 delta, and you see I take tau between delta and 2 delta, and 2 delta, the greater trait, is less than 3. That means that here the growth rate will always be positive. We will not have extinction. Okay, we try to understand this phenomena of re-emergence. So at the beginning, the exponent, so we said that we take the population with trait 0. Yes, I have my initial condition here. So the first exponent are 1 minus delta alpha, 1 minus 2 alpha. Okay, that's written here. So to simplify, let us assume that 2 alpha is less than 1. Okay. And so we compute. So we compute using the result I have shown here. So So at the beginning, what we have to do, so the dominant trait is 0, okay? And so what do we have? We have, if we want, we will compute. So what is the fitness of the trait delta in the population, the resident population with trait 0? So it's x is 0 minus delta plus tau, the sign of delta minus 0. Delta is positive, okay? So it's tau minus delta, and by assumption, tau minus delta is positive, okay? And so what does it mean? That means that beta 1s will be, so I follow the initial condition is 1 minus alpha plus, and the fitness is tau minus delta t, okay, s. But you have to compare it with the potential mutation which arise from the resident population from trait 0. So you have an order 1 for this population, and you multiply by the order of mutation rate. And so what you see that this is always greater than 1 minus alpha, you keep it, okay? That's beta 1 of S. Now, if you want to compute the fitness of 2 delta in this resident population 0, so you have exactly in the same way, minus 2 delta plus tau, and here it's negative, okay? So you have the potential candidate to be the equation for the exponent, the limiting exponent, could be if we forgot the immigration, okay, sorry, it's here. It could be, so at the beginning we have 1 minus 2 alpha plus tau so it's negative, so plus minus 2 delta s. But we have to compare this expression with the effect of the immigration, okay? And the immigration, so it arrives from these steps for the step, the trait delta, one corresponds to delta. And so you have this exponent, the initial condition, but you have to multiply this initial condition by the mutation rate, which will be minus alpha. So, and this quantity is greater than this one. So in this case, beta 2 of t will be equal to this expression, okay, because of the supremum which is here. And so we can continue. So that's the first step. And what you see is that, so you have, for this time S, you have beta 0, which is 1. And you have, so I have taken some specific delta here. And you have, so forget the third line, the fourth line. And you have beta 1, which is increasing because beta 1 tau minus delta is positive. And also you have beta 2, which is it should increase to yes, because sorry, so beta 2 t minus delta is positive, and so it also increases. And so the first time where there is some question is this one, where beta 1 arrives to 1, because you will have 2 dominant populations. So who will win? So we have seen that S delta 0 is positive. We can compute S 0 delta. And if we do the same thing, so now delta is x and 0 is y, so it's delta. And the sign of y minus x is negative, so we will have delta minus tau, which is negative. So that means that 0 will lose its dominant power. I mean, because the fitness of delta in the resident population 0 is positive, and this one is negative. Okay. And now we can continue to compute. So what is beta 0 of S? So after, so what is this time S1? This time S1 is a case where 1 minus alpha, where beta 1 of S1 equal plus tau minus delta S1 is equal to 1. Okay, that means that S1 equal to alpha over T minus delta. Now beta 0S, it was, initial condition was Y, and the slope is tau minus delta, so 1 minus tau minus delta S minus S1. Okay. So if we continue, we make two other computation for, of course, for the trait delta, we know now that delta is dominant. So the order of population will be 1. And for 2 delta, so we will compute now the fitness of S2 delta in the resident population, which is with trait delta now. So we have to compute this fitness, okay? So it's minus delta plus tau. And so if we compute the beta, we could say beta 2 of S. So that means the exponent given by the birth and death process without immigration. It should be, so we were at S1, you have to compute the value of beta 2 at S1, and you see that it is 1 minus 2 alpha plus alpha, 2 minus delta times S1. And so it's the initial condition it was 1 minus alpha plus 2 minus delta S. And if we compare with the mutation from delta, you will have only K times K minus alpha, which is K to 1 minus alpha. And this quantity is positive, so that's a good exponent beta 2. Okay? So that's the way. That's a little tedious. So I will not like the. So here I did that. So here is the simulation. So beta 0 is decreasing now. Beta 1 stay at the order 1, and until beta 2 attains 0. So you see how it is. So I just show you that we can continue, and so you see the picture, and you have first. So you continue the step, and at some point, so here it's the first step, you find that you are in a situation. So you have some sort of drawing, but here for the trait 0, you have the fitness of 0 in the population delta is delta minus tau. Delta is the optimum trait, and beta 2, the fitness of 2 delta is tau minus delta. So that means that at step 5, we are exactly at the step 2. And there is a periodic, in this case, but you have seen that we have a lot of assumption on this parameter. In this case, we have a periodic situation, and we can understand how it happens, okay, in the limit. We made other simulations. So here you see that with 4 traits, we continue. We have also a periodic behavior here. No, I think that there is only, sorry, 3 traits. So it's with exact value, the exact values are given here for delta, alpha, and tau, which are the 3 parameters which place together. Of course, we have seen that since the growth rate is always positive, we never go until extinction, which is for an exponent. Here we have the value of the exponent. So exponent 0 means extinction, and you have this periodic behavior. Okay, periodic behavior in this case. But you can see situation for here we have a lot of traits, and you see in this particular situation with different value of traits, you will have each trait emerge, stay dominant during some time, and then go to extinction. And so you have a succession of traits, but the subpopulation with such traits go to extinction. Okay, so that's such sort of simulation, and you can have simulation like that. So you see how full it is. And we see that the probabilistic approaches have their limit, but we try to do something. And the main result we have is that, essentially with the lemmas, we can understand what it happens, that this exponent process at the time scale logarithm of k, so convergence uniformly in probability to some curve. So it's for each I, so for each trait I delta, so to some curve beta is, but which is piecewise affine, since we have seen in the lemma that give you some piecewise affinity for the. So it's a continuous function, piecewise affine, and solution of a certain, I will write later, ODE system. And so we have the initial condition. And as we have seen, we can have change of slope for the exponent when a new exponent attains 0. So, okay, so that gives you a resident population. Or when a new exponent reaches 0, that gives extinction, as we have seen in the second simulation. Or the slope, as we have seen in the second lemma, the slope of an exponent which was driven by the fitness can change and then be driven by the mutation property. Okay, so you can. The proof is essentially to follow what I explained for three traits, but it's some part technical, but the idea is here. So what can be hard is that you can have situation where you have a resident population which are not dominant in the sense that the population size is not of the order k to the 1. Okay, so you can so you have also to play with such sort of population which are then they are killed by competition because the competition is of order k. Since we have to play also with that. But so we have this expression, and so how do we have seen in the example that you have a succession of deterministic intervals which are delimited by this sk, and which the sk are the time where the slope change. Okay, and so we can have a definition of this time sk, because you have seen in the example you have two exponents which arrive at the same value, and that's the place where things happens and competition happens between both traits. Okay, and so the function, so they are defined relatively simply. So because we have seen in the example that we have just to integrate the value of the fitness factor. So here for 0, 0 is special because 0 don't with this model 0 does not receive mutants. Okay, because the mutants are always driven in positive direction. So you have some specific equation for 0, which only depends on the fitness of the trait 0 in different dominant populations. And you have, so here I star of k is this trait, which is at some point the dominant trait. And here for beta I, you have to add the term which arises from mutation, okay? Which is the exponents of the population size immediately with the trait immediately before the trait I, so I minus 1, and times minus alpha, which correspond to the mutation. Okay, so you have some expression for this exponent. Okay, so now we wanted to obtain this re-emergence of 0 because you have seen this simulation. So we were able to study the three traits case, but there are a lot of possibilities if you change the value of tau, delta, alpha. But and we essentially obtain satisfying results, but for many for other traits, it's we don't see how to do with this method to obtain a complete picture of the different behaviors. And so we have, at least we gave an explicit criterion for the first reemergence of 0. So so we are in the situation where tau is greater than delta, as earlier. And so we have seen that beta 0 is affine, piecewise affine, and one can prove that the slopes are always defined by a value as S1. I mean, SK for beta 0, the slopes change at point SK, which are, where are they? SK is a K, it's written on the slide, but K alpha over tau minus delta. Okay, so you have an explicit value of the time where the slope of beta 0 is changing. And so we can compute beta 0 at some of these points. And you have an expression which depends on alpha, tau, and delta. And remember, tau minus delta is positive here. And so we can compute the minimal value. Because of course, if of the minimal values stay always positive, we will stay, we will not go to extinction. So we not, but so we will have different behavior depending on the value of beta 0 on the minimal value. So, but of course, these formula are essentially true, but before beta 0 attains 1 or before beta 0 attains 0. Okay, and there is another assumption here, since here you see, so remember that the growth rate is 3 minus x, and then if the growth rate becomes negative, we don't know what to do. So essentially, we consider the slope before this case. And so what we can prove is that if the minimal value of beta 0 on these times which correspond to changes of slope is positive, and if the trait is such that the growth rate is positive, then one can observe the resurgence of 0. That means beta 0 will take a positive slope and increase. And so we don't know at all under this condition if we will obtain a periodic solution as we observed in the three traits case. It seemed to be in the simulation, but in another simulation it can be different. So I don't know. And if the minimal value is less than 0, and if the growth rate is positive, so the trait is lost and there is extinction. Okay. And but see, if the growth rate is negative, so it seems that there is extinction of the population, but we have seen a simulation where the exponent, where the population re-emerge. So we honestly we don't understand this case. Okay. So for the moment, from the probabilistic point of view, we are in this situation, and we are not sure to be able to go further with this approach. There is
May I ask some questions?
Yes, of course.
Do you have a kind of an equation in the continuous case? I don't know if it makes any sense for the exponent beta.
So it's in continuous type. In continuous type.
Type, yes.
In continuous type. So no, we don't have expression.
The kind of renewal equation.
As it is the exponents, but so that's the underlying story. But we made some very informal computation, making delta tends to 0, and we seem to see something close to Hamilton-Jacobi equation. So
really? Okay.
Why we will change our point of view.
Thank you.
But not written, and I think it's not so easy because it seems that there are very specific and amazing behavior that there's some additional term we don't understand for the moment. So do you have any question on this? Yes.
So Sylvie, the simulations which you showed us some slides ago Were they based on an individual?
Okay.
So what was the population size? I mean, the N.
Which simulation you mean?
Yeah, well, some 5 size or the last ones which you showed us.
No, this one are not.
Right. I mean these are in the infinite population
this one
system,
are
right?
just to explain how it works at the
In the infinite
exponent
limit,
levels.
population
Yes.
limit.
Yeah.
But then, and also the one following, I mean, the next one, that's all in the infinite population.
That's exactly the dynamics of the limiting exponents.
Right.
But with such traits, a very large number of traits, of course.
Right. But you did have some simulations at the very beginning, right, which illustrated that could be reliable also in a system for finite n, right? When you have, because it's a law of large numbers limit, right? And the right, this is a law of large numbers limit.
The convergence of the beta I?
Yes.
Oh, I'm not sure.
Well, otherwise it would.
What do you,
well, there is no stochasticity left, right, in these periodic systems, right? It's a deterministic dynamical system, isn't it?
At the end, you mean?
Right.
Yes.
Right. And so still, it would be interesting maybe to see when you have a system with
when you say
a large population size,
that the limit is deterministic.
Right.
Okay.
Right. Right.
Mm-hmm.
And a question, another question. Could you remind us of the scales of the selection and mutation? Is this a strong selection regime or a weak selection regime or something in between?
Here
you are on another time scale, right? This log. The time scale is the log.
Yes, but the competition death rate is always C n over k. That's why, in fact, the competition only acts on dominant population, where for the resident population, if the population size is of order k. If the population size is less than k, it's k to the beta less than 1, you don't see anymore this competition.
Right.
So you have two, in fact, you have two situations. Either in the fitness, depending on the population size.
Right.
But,
and on the generation scale, the mutations would come rather frequently, right? In the entire population.
So mutations, they arrive. The individual mutation rate is k minus alpha.
Yes, but
alpha is less than 1. So that depends. If the initial population is dominant population, it will be k 1 minus alpha. But if not, and that explains the computation I did.
Right.
It's if you are at for the trait a plus 1, you have to consider the population size of the trait, which is I, and I plus I plus 1 delta. And then you will have of mutation on the dynamics of.
As you said, it's similar to the direct Maybury scheme, right?
Yes. But here that we have this trade-off between competition and transfer. They don't have. They are in a finite population model.
Okay, so Pascal has a question.
Yeah, I think I have a question a bit similar to Anton's. So could you please go back to the pictures of the simulations in the case tau equals 0.7?
Oh, which one?
Yeah, I'm able to remember one number.
The first one? No, I don't know.
So the simulations of the stochastic model of the original model.
The original
in the case tau equals 0.7.
Yeah. Oh yes, this one.
Right.
Okay.
Right. Exactly.
Yeah.
So if I remember, if I understand correctly, and that's also what you indicated, is that in the large population size limit, the log density should converge to some Hamilton-Jacobi equation, right? So in particular, this extinction or non-extinction, this is a finite k artifact, right? So if k, if you did you do like simulations with k a million and where you did not see any
No,
So with this particular parameter,
I don't think it's an artifact.
Well, it's reality. It's not an art. It's finite K reality.
okay.
It's not,
I crossed the word artifact, so, but it's a random event which occurs if K is finite, and if you take the simulations with K larger and larger, then this event probability becomes smaller and smaller.
What do you think is that the probability to observe some few individuals could disappear? But no, it does not disappear. We have seen that.
No, I mean the probability of the two bottom.
Of this one.
Yes. This will go to 0 when K goes to infinity, right? With this particular parameter.
So certainly.
Okay.
So you're right in the sense that in microbiology you have a lot of that depends on the situation, but you can have a lot of bacteria, and K can be very, very, very large.
Is there a question in the chat? Another question in the room?
So that's why, since we were, that it seems to be hard to go further with probability tool, and since we made this sort of computation, so first I am convinced that this point of view to consider the exponent of this small population or not small can be interesting, but so we thought to be obliged to consider perhaps simpler model, but in which we could associate this exponent convergence to Hamilton-Jacobi equation. And so that's why I will develop tomorrow. That means that we will be in a very, very simpler case. So we for the moment, because in fact, up to my knowledge, but we have never seen paper explaining, as Sepide explained, the Hamilton-Jacobi equations directly from the individual-based system. That's the subject of the lecture tomorrow, is how to see. So we will stay in the time scale logarithm of K. But here we wanted first to arrive on the first Hamilton-Jacobi equation obtained by the group of Pertam, Bard, Miralmi, which was not with an assumption on the probability mutation, but on the step of mutation. So you have always this play between rarity and size of mutations. And so what we will change our mind. We will consider at the beginning a discretized space, but we will make, as we say, the mutation, the discretization step goes to 0 at the time scale logarithm of K, but we will assume very small an assumption on the size of the mutation. So I think I can finish here.
Okay, thank you, Sylvie.